I have an expression for electric current in terms of drift velocity and number density of free electrons. This relationship is fundamental to understanding how electric current flows through conductors. First, let's visualize what's happening in a conductor. Here's a section of a conductor, like a wire. Inside this conductor, we have many free electrons that can move around. When we apply an electric field, these electrons develop what we call a drift velocity in the direction opposite to the electric field. Let's define our variables. We'll use n for the number density of free electrons, a for the cross-sectional area of the conductor, v_e for the drift velocity, and e for the elementary charge of an electron. Now, let's consider what happens in a small time interval t. The electrons will move through a volume equal to the cross-sectional area, a times the distance they travel, v_t. The number of electrons in this volume is the number density n times the volume. To get the total charge that passes through in time t, we multiply by the charge per electron, E. Current is defined as the rate of flow of charge, which means we divide the total charge by time. This gives us our final equation, I equals NA v_t. Let's understand what this equation tells us. The current increases if we have more free electrons per unit volume, higher N, a larger cross-sectional area, bigger A, faster moving electrons, higher drift velocity v_e, or if the charge per electron, E, were somehow larger. This equation is particularly useful because it connects the microscopic behavior of electrons to the macroscopic current we can measure. In practice, we often use this to find the drift velocity of electrons, since we can measure the current, and we know the other quantities. Remember, while individual electrons move quite fast randomly, the drift velocity is typically very small, on the order of millimeters per second. This is because electrons frequently collide with the atoms in the conductor, resulting in this slow net movement despite their high individual speeds. Today we'll derive the expression for electrical conductivity of a material. Let's start with our fundamental expression for electric current in terms of drift velocity. Let's first visualize what's happening in a conductor. Here's a piece of conducting material. Inside, we have free electrons that can move through the material. When we apply an electric field, these electrons begin to drift in a direction opposite to the field, creating an electric current. Let's start with Ohm's law. Voltage equals current times resistance. We know that resistance depends on the material's resistivity, length, and cross-sectional area. The electrical conductivity sigma is defined as the inverse of resistivity. This gives us sigma equals 1/ρ. Now, a key relationship is that the drift velocity of electrons is proportional to the electric field, where the constant of proportionality is the electron mobility mu. The electric field can be expressed as voltage over length. This gives us E equals V/L. Substituting this into our drift velocity equation, we get that the drift velocity equals mu times V/L. Now let's substitute this expression for drift velocity into our original current equation. This gives us I equals NA mu V/L times E. We can rearrange this to express current in terms of voltage. From our definition of conductivity, we know that current can also be expressed as sigma times V/L times A, setting these equal to each other. Sigma VA/L equals NA mu VE/L. The voltage, length, and area cancel out on both sides. And there we have it. The electrical conductivity of a material is equal to the product of three terms, and the number density of free electrons, mu, the electron mobility, and E, the elementary charge. This elegant expression shows that conductivity depends on both the number of available charge carriers and how easily they can move through the material. This expression is fundamental in understanding the electrical properties of materials and explains why some materials are better conductors than others. Let's analyze two cells connected in series. Here's cell 1 with EMF E sub 1 and internal resistance R sub 1. And here's cell 2 with EMF E sub 2 and internal resistance R sub 2. When connected in series, the negative terminal of one connects to the positive of the next, forcing current flow in the same direction. The equivalent EMF is simply the sum of the individual EMFs. This is because the voltages add up. Similarly, the equivalent internal resistance is the sum of the individual internal resistances. the current passes through each resistance consecutively. Therefore, for series-connected cells, we simply add the EMFs to get the equivalent EMF, and we add the internal resistances to find the equivalent internal resistance. Let's analyze a circuit with two cells connected in parallel. This is cell 1 with EMF E and internal resistance R. And this is cell 2 with EMF E2 and internal resistance R2. Let's assume, for simplicity, that both cells have the same EMF. This means E equals E2. The equivalent EMF, in this case, is simply the common EMF. Now, let's find the equivalent internal resistance. For resistors in parallel, we add their reciprocals. Solving for R underscore AQ, we arrive at this expression. To summarize, for two identical cells connected in parallel, the equivalent EMF is simply the EMF of each cell, and the equivalent internal resistance is given by this formula. Today we'll learn about finding the balance condition for a Wheatstone bridge network using Kirchhoff's laws. Let's first draw our Wheatstone bridge circuit. We have four nodes, A, B, C, and D. These nodes are connected by four resistors, R1, R2, R3, and R4. A battery is connected between nodes A and C, and a galvanometer is connected between nodes B and D. When the bridge is balanced, no current flows through the galvanometer. Let's label the currents in our circuit. I1 flows through R1, I2 through R2, I3 through R3, and I4 through R4. Let's apply Kirchhoff's voltage law to find the balance condition. First, let's look at loop ABCDA. According to KVL, I1 R1 minus I2 R2 equals 0. Similarly, for loop CBDC, I3 R3 minus I4 R4 equals 0. When the bridge is balanced, the current through the galvanometer is 0. This means I2 equals I3 and I1 equals I4. Let's substitute these conditions into our equations. Since I2 equals I3 and I1 equals I4, we can conclude that R1 over R2 equals R3 over R4. This is the balance condition for a Wheatstone bridge. Let's solve a problem about electron drift velocity in a copper wire. We need to find how many electrons pass through a cross-section of the wire in 1 second. Let's first visualize what we're working with. Here's our copper wire. It has a length of 0.021 meters and contains 3 times 10 to the 22nd free electrons. These electrons move with a drift velocity of 2 times 10 to the negative 5th meters per second. To solve this problem, let's focus on a cross-section of the wire. When we look at a cross-section, we're interested in how many electrons pass through this plane in 1 second. To find this, we'll use the formula. N equals N times A times VD, where N is the electron density, A is the cross-sectional area, and VD is the drift velocity. First, let's find the electron density. We know we have 3 times 10 to the 22nd electrons in 0.021 meters of wire. Dividing these numbers, we get 1.4286 times 10 to the 24th electrons per cubic meter. Now we can plug this density and the drift velocity into our equation. We'll assume a cross-sectional area of 1m squared. For simplicity, this simplifies our calculation. Multiplying 1.4286 times 10 to the 24th by 2 times 10 to the negative 5th, we get 2.858 times 10 to the 19th electrons per second. Therefore, approximately 2.857 times 10 to the 19th electrons pass through any cross-section of the wire in 1 second. Let's solve a problem about electrical resistance in a copper wire. We'll find the required length of wire for a specific resistance, and then see how doubling the diameter affects that resistance. Here's our problem. We have a copper wire with a diameter of 0.5 millimeters and resistivity of 1.68 times 10 to the negative 8 ohm meters. We need to find what length will give us a resistance of 2 ohms. Then we'll see how the resistance changes when we double the diameter. Let's start by visualizing our wire. Here's our copper wire with diameter D. We need to find its length L to achieve our desired resistance. To solve this, we'll use the resistance formula. Resistance equals resistivity times length divided by area. For a circular wire, the area is pi times diameter squared divided by 4. Let's calculate the area first. We plug in our diameter of 0.5 millimeters, making sure to convert it to meters. This gives us an area of approximately 1.96 times 10 to the negative 7 square meters. Now we can solve for the length. Rearranging our resistance formula, Length equals resistance times area divided by resistivity. Let's plug in our values. Resistance of 2 ohms, our calculated area, and the resistivity of 1.68 times 10 to the negative 8 ohm meters. Calculating this out, we get a length of 23.8 meters. Now, what happens when we double the diameter? Here's our wire with twice the diameter. When we double the diameter, the area increases by a factor of 4, since area depends on diameter squared. Since resistance is inversely proportional to area, when the area increases by a factor of 4, the resistance decreases by a factor of 4. This means our new resistance will be 0.5 ohms. So to summarize, we need a 23.8 meter long wire to get a resistance of 2 ohms, and doubling the diameter reduces the resistance to 0.5 ohms. Let's solve a problem about battery internal resistance. We have a battery of 6 volts that gives current of 2 amperes when connected to a resistance of 2 ohms. We need to find the battery's internal resistance, terminal potential difference, and lost voltage. Let's start by drawing our circuit. Here's our battery with EMF of 6 volts. Every real battery has some internal resistance, which we'll call R, and here's our external resistance of 2 ohms. The current of 2 amperes flows through the entire circuit. To find the internal resistance, we'll use Ohm's law. The total EMF equals current times the total resistance. The total resistance is the sum of the external and internal resistances. So we can write 6 volts equals 2 amperes times the quantity 2 ohms plus R. Let's solve this equation. First, distribute the 2. 6 equals 4 plus 2R. Subtract 4 from both sides. 2 equals 2R. Finally, divide both sides by 2. R equals 1 ohm. Now, let's find the terminal potential difference. This is the voltage across the external resistance. Using Ohm's law, Vt equals IR, which is 2 amperes times 2 ohms, giving us 4 volts. Finally, let's calculate the lost voltage. This is the voltage drop across the internal resistance. Using Ohm's law again, V lost equals IR, which is 2 amperes times 1 ohm, giving us 2 volts. Let's verify our answer. The EMF of the battery, 6 volts, should equal the sum of the terminal voltage and the lost voltage. Indeed, for volts plus 2 volts equals 6 volts. So our final answers are: the internal resistance is 1 ohm, the terminal potential difference is 4 volts, and the lost voltage is 2 volts. Let's solve a problem involving 2 cells connected in parallel with an external resistor. We have 2 cells, one with an EMF of 3 volts and internal resistance of 1 ohm, and another with 4 volts and 2 ohms internal resistance. These are connected in parallel to a 10 ohm external resistor. Let's draw our circuit diagram. Here's our first cell with EMF E1 equals 3 volts and internal resistance R1 equals 1 ohm. And here's our second cell with EMF E2 equals 4 volts and internal resistance R2 equals 2 ohms. Finally, we have our external resistor of 10 ohms. To find the potential difference across the external resistor, we first need to find the equivalent EMF of the parallel combination. The equivalent EMF is given by E1 times R2 plus E2 times R1, all divided by R1 plus R2. Next, we need to find the equivalent internal resistance. 4 cells in parallel. This is given by R1 times R2 divided by R1 plus R2. Now we can find the total resistance in the circuit. This is simply the equivalent internal resistance plus the external resistance. 2/3 plus 10 equals 32/3 ohms. Using Ohm's law, we can find the current through the circuit. Current equals equivalent EMF divided by total resistance. Finally, we can find the potential difference across the external resistor. This is simply the current times the external resistance. Therefore, the potential difference across the 10 ohm resistor is 3.125 volts. Let's analyze a Wheatstone bridge circuit and determine if it's balanced. We'll also find how to adjust the resistances to achieve balance. Let's first draw our Wheatstone bridge circuit. Here's our bridge configuration with 4 resistors. We have our 1 equals 10 ohms, our 2 equals 20 ohms, our 3 equals 30 ohms, and our 4 equals 50 ohms. The bridge is connected to a voltage source, and we have a galvanometer connected across the bridge. For a Wheatstone bridge to be balanced, the ratio of resistances in one arm must equal the ratio of resistances in the other arm. That is our 1 over R2 must equal R3 over R4. Let's check if our bridge is balanced. On the left side, R1 over R2 equals 10 over 20, which simplifies to 1/2. On the right side, R3 over R4 equals 30 over 50, which simplifies to 3/5. Since 1/2 is not equal to 3/5, our bridge is not balanced. To balance the bridge, we can adjust either R3 or R4. Let's first calculate what R3 should be. If we keep R4 at 50 ohms, R3 should equal R1 times R4 divided by R2. That's 10 times 50 divided by 20, which equals 25 ohms. Alternatively, we can adjust R4. If we keep R3 at 30 ohms, R4 should equal R3 times R2 divided by R1. That's 30 times 20 divided by 10, which equals 60 ohms. So to summarize, our bridge is not balanced in its current state. To balance it, we can either adjust R3 to 25 ohms while keeping R4 at 50 ohms, or adjust R4 to 60 ohms while keeping R3 at 30 ohms. Either adjustment will make the bridge balanced.